Okay, now our last part of what we need to cover for power series, or for sequences in series, and actually this has to do with when we use polynomials. So we know that a power series, if it goes to infinity, can be exactly equal to a function, where a polynomial is a way to approximate the function. So this, what we're going to talk about, is the Lagrange bound, or the Lagrange error bound, or sometimes it's just called the Taylor theorem remainder, or the Taylor's remainder. And so we know that if we use a polynomial, like a Taylor polynomial, it's only approximately equal to the function value, so that means there must be some sort of remainder left. So we've got the function here, and it's going to equal the polynomial that we have plus some sort of remainder. And so if we just kind of solve that for the remainder, it means if you take the function minus the actual function value minus the polynomial, you get the remainder. So in words, this is how we're finding the remainder. It's just the function minus the polynomial approximation. Well, the way that puts that in kind of in algebra is we're subtracting, and here it's written polynomial first and function last, but we're absolute values, so it doesn't matter which way it is. And so it's actually very similar to when we did alternating series, because you remember, if you do an alternating series and you add up, say, the first 7 terms, then the largest your error can be is whatever the 8th term is, whatever that value is. That's the most you can be off, and we found an interval. So this is very much like that. If you see here, we have n plus 1, n plus 1. So we're basically at the n plus 1 term. The difference is there's a z here. And that's not an x, and that's not an x on purpose. And that's actually what is basically, we want the value. So the z is the value that maximizes that n plus first derivative. So what we're looking for is a value of x that would actually give us the most that derivative could equal. So we're looking for the maximum there. So that way we get the maximum error that we could have. All right, so let's go through a couple of things, looking at it kind of written out. So again, here's your Taylor polynomial. We know that. That's the function at c plus the first derivative at c times x minus c, etc., etc., and then plus the remainder. And then the remainder is that we just talked about. So again, it's basically the next term. So you add it up, 7 terms, and the remainder is basically the 8th term, but it's a bound on it. So it's not the actual error, it's the most it could be. And then this right here, we want to be the largest value that derivative could have. And so we'll talk about how to do that as we look through some things. And so enjoy your goofy picture there on the bottom. All right. So now, the irony about this is, today, if I wanted to approximate a function, I could just type it in the calculator and I get an approximation. But these types of ideas are super important. We've talked about it a little bit, but like if you're trying to program a computer, you need to know how much error you're allowing, and so on. And so there's a lot of reasons that this is really important that are kind of hard to see now. So just assume that we realize that in a lot of cases we could just put it in the calculator, but we're still wanting to know how accurate are we if we were to add it up and do it by hand. Now in this example, we don't even know what the function is. And so definitely we would have to go through this process. Okay, so we're saying that we've got a function that has 5 derivatives. And then they're telling us that the 5th derivative, the value of it, is less than 0.2. So they're telling you that it is at most, well, just under 0.2. So that's that thing that we need for that remainder. We want that maximum value that derivative could have. Well, that's giving you kind of that bound. And it's telling you that's true for the interval 2 to 3, which is what we're interested in here. And so we're going to use a fourth degree Taylor polynomial. So fourth degree means that we're going to do P4 of x. Sometimes you'll see T for Taylor, but I tend to just always use P for P4. So we're using the fourth degree Taylor polynomial around the center c equals 2 to estimate this function. And we don't know what the function is. We just know that we're trying to figure out what is the function value at 3, and we're going to use this polynomial to give an estimate of the answer. And then we want to know how accurate it is. Okay, so if you do the fourth degree polynomial, then that means that the remainder we're interested in, so we know this is approximately equal to f of x. So we know that the remainder, well, the way we put the remainder is we call it R4, and we're doing it at 3. The remainder will be different at different places. Remember that the polynomial is more accurate when you are close to the center. So when you get further from the center, it's less accurate. So it makes a difference where we're finding that remainder. So we're saying this is the remainder if you're evaluating the function at 3, and you're using this polynomial to do it. Well, the remainder is actually going to be the next derivative, so the fifth derivative at some z over, well, if you're on the fifth term, it'll be 5 factorial, and then it will be x minus c. Well, x here is 3 because that's what where we're evaluating it, so this is x. And then we know the center is 2, so that's 3 minus 2 to the fifth, because we're on the fifth term here. So we know this is the form of the remainder. Well, and so again, this 3 is where we got that, and then the center was given. So they told us, though, that we know that the remainder, or the fifth derivative, is less than 2. So that means that this answer right here is less than or equal to, if we were to substitute 0.2 in over 5 factorial times 1 to the fifth, because that's what this is going to be, 1 to the fifth. So that's what that bound is giving us. So we're saying that we don't know the exact remainder, but we know for sure it's less than that number. Okay, so that's what we're interested in. So we know it's less than that. If you take your calculator and put that in the calculator, you're going to get 0.00166. Now remember, you can store those things in your calculator if you want to use them later. You could just store it as R or A or whatever you want to store it as, or you can always call up that line again when you need to use it. So basically, this means that if we use polynomial with 4 terms in it, evaluated at 3, it is within 0.00166 of the actual function value. So it's telling us this is how accurate we are. Okay, so even just 4 terms were that accurate. Now, suppose that the fourth derivative, or the polynomial, when you plugged in 3, so if we knew what it was and we have the Taylor polynomial and we plugged the 3 in, the answer is 1.763. So we're going to give an answer of what interval the actual value of f of 3 must lie. Well, f of 3 must be somewhere between whatever this value is plus or minus that remainder. And that's what we know is going to be the answer. So we know worst case scenario, we are 1.763 plus or minus 0.00166, which again you could store so you don't have to type all that. So we know we're somewhere in that range, and if you type that in your calculator, you're going to get somewhere between 1.7613 and 1.76466. So if you do the math there, and you should practice that on your calculator, but that's the interval. So what we're saying is the actual value, function value, at 3 is somewhere in that interval. So then the next question says, okay, well, could f of 3 be 1.778? And then why or why not? Well, remember, 0.00166 is the largest, the worst we could be. That's the most we can be off. And we get this answer. This is the range that we know the actual answer is definitely in there, because we found the most, the biggest amount we could be from the real value. Well, 1.778 is not in that interval. So my answer here would be no. 1.778 is not in the interval. That's the reason that's not possible. That cannot be the function value. Now D says, could f of 3 be 1.764? Well, look at your interval. Well, 1.764 is in there. So yes, 1.764 is in the interval. So that is a possible value for the function because it is in that interval. So that's all we're trying to do, is give a range of values that says, okay, our real function value is somewhere in there. And if you look at it, we're pretty close. Okay, even with 4 terms, we were pretty close. Okay, so now this one says find the 5th degree Maclaurin polynomial for sine, then use that polynomial to approximate sine of 1. Now again, you could just take your calculator, type in sine of 1 and get an approximation. But there are more uses for this idea, so we're going to go through the process. Now, we're not going to find the polynomial by doing all the derivatives right now, because we know this one. This is one of those I told you you need to memorize. And so we know that sine of x is approximately x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, because it said 5th degree polynomial. So 5th degree means 5th, right here, 5th derivative, 5th term, okay? Not the 5th term, but up to the 5th degree. So that's my approximation. So that means that sine of 1 is approximately equal to 1 minus 1 over 3 factorial, which is 6, plus 1 over 5 factorial, which would be 120. And if we were to add all of those up, we'd get 101 over 120, and you can get your common denominator there. But we want to put that in the calculator because we want to have an approximate, because it says 3 decimal places. So I'm going to put more than 3 decimal places. But that's what we get when we do that in the calculator. And so this is P5 at 1. That's the polynomial where we went to the 5th degree polynomial evaluated at 1. So that's our guess for what sine of 1 equals. Well, let's now talk about what that remainder is and how much are we off. So that means if we did 5th degree, the remainder is written as R5, and then again at 1, because it'll be a different remainder at different places. Absolute value of the 6th derivative at some z. That's where we don't put an x, because that's saying whatever it is that makes that the largest value I can have there, divided by 6 factorial times x is 1, center is 0, because it was a Maclaurin polynomial, to the 6th. So knowing that format of those polynomials is really important here. Well, now the problem is I got to figure out a bound on that. So I've got to figure out somewhere what is the maximum value the 6th derivative could have. So now we got to figure out what's the 6th derivative. Okay, so over here to the side, let's just write kind of small. F of x is sine. F prime is cosine. F double prime would be minus sine. F triple prime would be minus cosine. F fourth prime would be sine again. So now we're back to that. 5th derivative then would be cosine. 6th derivative would be minus sine. And the reason I needed that is I needed to know the 6th derivative. I need a bound on that. Okay, so we got the 6th derivative is equal to minus sine of x. So we want to know what is the largest value that could have if you are at 1. Well, guess what the largest value would be if x is 1? It would be minus sine of 1, and then absolute value that. But the sine of 1 is what we're trying to figure out. So that doesn't help us. We can't use the value we're trying to figure out to put in for the value we're trying to get the remainder. That doesn't make any sense. But remember, this is a bound on our error. It's not saying this is the error or this is the remainder. We're saying this is the most it could be. Well, it's a sine function. So what's the largest value, because we're in absolute value, that sine could ever have? Well, that would be 1. So we can simply put a 1 there. We'll put 1 for f prime of 6 over 6 factorial times 1 to the 6th. So we're not always going to pick exactly the maximum, but we just want to know, if we can't use the exact value of the maximum, we just want to be sure we're choosing something that's a little bit bigger. I mean, we could have picked 12, but then we would be a lot off. So we want to pick something close, but we may not be able to use the exact thing. Well, we know for sure the remainder is less than that then, because 1 is definitely bigger than whatever the value is for sine of 1. And so we can't be more than that off. This is the most we could possibly be off. And if we do that in the calculator, we get 0.001389. So this is the max error. Okay, so that's the most we could be off using this value right here, adding up, doing P5. The most we are off from the actual value is 0.001389. Then it says, okay, now use your interval your answer that you found to find an interval. So that means we're going to go from the estimate we got using the polynomial, 0.841667, and then it's plus or minus this maximum error that we have. So in your calculator, just do plus and minus that, and you get 0.840278 up to 0.843056. So you are anywhere within that interval. It is the actual value of sine of 1. So then the next question says, could sine of 1 equal 0.9? Well, look at your interval. 0.9 is not in there, so our answer would be no. 0.9 is not in the interval. Because remember, this is the worst, the biggest interval we can have. That's the most we can be off. So there's no way it's 0.9. We can't be more off than that. So it's got the actual answer somewhere in that interval. And if you just do sine of 1 in your calculator, you can see it's right perfectly in that interval. Okay, so let's go to the next example. So here's a no calculator problem. So we want to write a 4th degree polynomial, Maclaurin, for e to the x. So Maclaurin means that c is 0, centered at 0, and we're going to write the polynomial. So we know this one, again, this is one we're supposed to know. It says 4th degree, so we go until we get an x to the 4th. So that's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. Got to go all the way till you get an x to the 4th to get the 4th degree polynomial. Then they want to use that polynomial to approximate e. Well, if we're approximating e, that means x is 1. It's e to the 1st. So we know e to the 1st is approximately 1 plus 1 plus 1 over 2 plus 1 over 6 plus 1 over 24. And then if we go get our common denominators and everything, we get 65 over 24, which is about 2.70833, putting that in your calculator. So that is our guess for the value of e. Now, we know we're not right. So let's look at the remainder theorem. So the remainder, so it would be R4 at 1, because that's the number we used for x, and 4 because it was 4th degree. That remainder is at most, or the remainder is exactly f 5th degree at some z, but the z is what we're not going to ever know, so we're going to make a bound on this. We're going to say, okay, well, the worst that number could be is this, so we're less than that. And then you'll have 5 factorial, you'll have 1 minus 0 to the 5th. Okay, so it's always 1 degree higher, and just write that format. Well, we know that's less than or equal to. Well, again, we have to know something about what's the fifth degree, what's the biggest value you could have. Well, if you take e to the x, what's the derivative? What's the first derivative going to be? E to the x. We take the second derivative, we get e to the x. We take the third derivative, we get e to the x, etc. So the fifth derivative is e to the x. And we're talking about what is the worst case scenario in the interval from basically 0 to 1, because 0 is the center and 1 is where we're approximating it. Well, that means it has something to do with e to the first. Well, if you look at the graph of e, we're talking about going between 0 and 1. Well, if we're at 1, then we know we get e. And we know e is 2.7 something. So for sure it's less than 3. So we'll just use 3 there. We know for sure that that maximum value of the fifth derivative has to be less than 3. And then over 5 factorial, and then that's 1 to the fifth. So we don't need to have anything there. So that's what we're doing. Again, we're getting a bound. We're not getting an exact answer. We're getting a bound. So we know the worst case scenario is this is the remainder. And so this is going to be 0.025. And so we want to figure out now in part B, what is the interval such that we know e is somewhere between there. So we know that we have our estimate, 2.70833, and it's plus or minus this error. So that's going to give us an interval anywhere between 2.68333 and 2.73333. And we know that the value of e is about 2.71828, etc., which is right in that interval. And so that's the idea. And that's what we're doing. We're just giving a range for where the answer is. Okay, so here we have another one that doesn't give us the function, and this is our last example. It just gives us a bunch of information. And so we don't have to have the function in order to answer this question. And this is probably a very reasonable question for the AP test, because they're not giving you a function you can just plug in the calculator to get an answer to make a good guess here. You've got to actually understand what's going on. So the first thing it says to do is write the third degree Taylor polynomial for this function. And so we know the actual function, whatever it is almost this. It's approximately this third degree polynomial. Well, how do we write a Taylor polynomial? Well, we take the function, and we're doing this one centered at 2. And we know it's centered at 2 because it says about x equals 2, and they're using 2's here for everything. So we know the center is at 2 here. So we take the function value at 2, and that's the first term. Well, that's 6. Plus, then we take the first derivative at 2, which is 4, times x minus the center, which is 2. Plus, we take the second derivative evaluated at 2, which is negative 7, over 2 factorial x minus 2 squared, plus third derivative 8 over 3 factorial x minus 2 cubed. It's always the same format, the coefficient over the factorial and power that all agree. And so there's your polynomial. Now you could leave it like that. You could simplify it a little bit. Never distribute. We want to leave it with the x minus 2's in it, but we might want to just clean up the numbers a little bit because we're going to have to use a calculator here. So we could put minus there since it's negative 7 over 2. And then this would be 8 over 6, which is 4/3 x minus 2 cubed. Now always, again, leave the x minus 2. You don't want to multiply that out. Leave that just like it is, because what we're getting ready to do is use it to approximate f of 2.3. Well, we know f of 2.3 is approximately this polynomial evaluated at 2.3, which is going to be 6 plus 4 times, well, x is 2.3, so I'm going to plug 2.3 in there. Well, 2.3 minus 2 is just 0.3. So every time inside your parentheses, every single one of those will just be a 0.3. So we'll have minus 7/2, 0.3 squared, plus 4/3, x minus, or not x minus 2, 0.3 cubed. Okay, so we're just recognizing that we plug in 2.3. 2.3 minus 2 is 0.3. So there's your polynomial. Now you would take that, put it in the calculator, so you should practice that. Put it in your calculator and you will get approximately, or this is 6.921. So that's what it said first. Just give that approximation to 3 decimal places. And so there we go. Now it says, okay, so let's say that we know that the fourth derivative satisfies this inequality. We know that the fourth derivative is less than or equal to 9 in the interval 2 to 2.3. Now we want to write that error bound. So we want the remainder for a third degree polynomial at 2.3. Again, remainder is different everywhere you are. The further you go from 2, the more you'll be off. The closer to 2, the more you'll have the closer value quicker. So we want the remainder at 2.3, because remember we did a third degree polynomial, so this is always going to agree. It's going to be absolute value. Well, it's going to be the fourth derivative at some z divided by 4 factorial x, which is 2.3, minus the center, which is 2, to the fourth. So that's what you're going to have for your format for your remainder, always following that Taylor polynomial. So we know that's got to be less than or equal to, again, here they told us the fourth derivative at x is always less than or equal to 9. So that can be kind of put in place of that. We'll put a 9. Because we know that that's the most it could equal. And that's what we're aiming for, is a bound on our error. So that's 9 over 4 factorial times 0.3 to the fourth. So again, get your calculator, do that in the calculator, and you get this value. And make sure you're practicing and do some of those, especially those of you that don't use your calculators enough, to make sure you know how to do it. And then we want to give, again, the interval where we know the actual function value lies. Well, our estimate was 6.921, plus or minus this error we just found. And so our interval is going to be 6.91796 to 6.92404. So somewhere in there is the actual value of f of 2.3. And then the last thing it says is, based on the information we just found, could f of 2.3 equal 6.992? Could that be right? Look at the interval. And you can see the answer is no. 6.992 is not in the interval. Because again, this interval represents the maximum amount I could be off from the actual value. And 6.992 is outside of that. It's even more than that. So it cannot be that value. So that's it for Lagrange error.